Hi guys, so this is question 2 of the 2019 Mechanics 3.4 exam. So we're just going to continue off from part 1. So this question, part 2, will be on rotational motion. So let's just get started. So we've got 3 children are playing on a merry-go-round with a rotational inertia of 271. And then we've got this, each child has a mass of 28 kgs. So that's important. And the merry-go-round has a radius of 2.10, which is also shown here. So assuming the rotational inertia of a child's mass on the edge of the disc is given by I, which is the inertia, equals mr squared, which is the mass times radius squared, show that the rotational inertia of the system is 641. So the system is everything within the sort of context. So the system is the merry-go-round and the children, all 3 of them. So we're trying to find the total rotational inertia. That's what we're trying to do. So we've got the formula here. Now this formula is not on the formula sheet, so you might have to memorize it for some questions, but they've given it to us here. We already know the rotational inertia of the merry-go-round. It's 271. So that means the inertia of the system is just going to equal the inertia of the merry-go-round. I'm just going to call it mr, plus the inertia of the children. Right, all 3 of them, not just one. So I system equals, this is already here, 271. Plus, now we have to find these three children, so it's just going to be their inertia times 3. So I'm just going to put a bracket plus 3 times, they all have the same mass. As you can see, each child has a mass of 28 kgs. 28 times 2.1 squared, and that should give you an answer of around 641.44 kgm squared. Now this is a show question, so you do have to have the unrounded answer. It's really important that you have this unit, or else you might not get the mark. And then obviously that just equals 641. So this is an achieved level question. If you are able to correctly have the working and show that it equals 641, you'll get an achieved. Okay, next question. The total energy of the system is 388 joules. Show that the angular velocity of the system is 1.1 radians and the linear velocity of one of the children is 2.31. So again, we've got a couple show questions. Okay, so with this information, if we go to our formula sheet, there is an equation we can use to do this, and that is the rotational kinetic energy is equal to half inertia and angular velocity, or omega squared. And we have all the stuff we need to rearrange to get omega, so we can rearrange this. So first of all, 2 ek rot, so we're going to move the half to the other side, equals I squared. And then if we jump up here, that's going to be 2 ek. I'm just going to get rid of the rot, divided by I equals omega squared. So omega equals the square root of 2 ek divided by I. So we know what the rotational kinetic energy is. It's here, the 388 joules. Now remember, that's the system. So we also have to use the system's inertia, which we found up here. So with these show questions, they usually hint the sort of values that you are going to end up using in the next question, or else they wouldn't make you show something. So angular velocity equals 2 times 388 divided by the inertia of the system, which is 641. You can use the unrounded answer of 44. So that should give you an answer of somewhere around 1.10 radians. Just include the unit. So the next one is the linear velocity. So that equation is also on your formula sheet, and it is this. So you've got your linear velocity equals your radius times angular velocity. So don't get confused between these two. They are different types of velocity. So we can just simply plug in the values. So the radius is up top. It is 2.1, I believe. Yep, the radius is 2.1 up there. So if I switch back to my pen, we can put in 2.1 times the angular velocity we found from the previous question, 0.1, and that is going to give you 2.31, something like that. Okay, so two very easy show questions. I think this question is worth a merit in total. So if you are able to prove both of the correct answers with the correct working and correct working, you will get a merit. Or you could prove either one of them is worth an achieve. So any one with working, obviously. Okay, let's move on. One child drags her foot on the ground to bring the merry-go-round to a stop in 2.8 seconds. Calculate the amount of torque produced by the foot. Alright, so there are a couple things. So we know the torque formula is equal to the inertia and the angular acceleration. So the first thing we're going to do is we've got the inertia of the child. We just need to find the angular acceleration. So if you go on your formula sheet, you'll see that the angular acceleration equals the change in angular velocity over the change in time. So that's going to equal the, well, it's just going to equal 1.1, what we found before, divided by 2.8, which is the time it takes to stop. And that's going to equal 0.393 rads to the minus 2. Now I've got that. So torque equals. Now this is the one of the ways people mess up is that they use the inertia for only one of the child. So they might only use the inertia for one child. You have to consider the inertia of the entire system, right? Because she's stopping the merry-go-round and the other children from spinning, right? So you have to use the inertia of the system and not the individual components times the angular acceleration. See, we just found. So that's going to equal 641.44 times 0.393, and that's going to equal 252 Newton meters. So this is a merit question again. If you get the correct torque with correct working, you get a merit. If you are able to find the angular acceleration or you calculate the torque correctly with an incorrect angular acceleration value. So let's just say achieved is up to here. Alright, I think we have one more question to go. Yep, so last question. Part D. The children get the merry-go-round spinning once again at a constant angular speed. Then each child moves inwards. Alright, that is the key word right there. Moves inwards towards the center of the merry-go-round. Using physics principles, explain the effect this has on the rotational energy of the system. So this is sort of one of those repetitive explain questions where you have to sort of tie multiple concepts together to form your answer. So if I just draw the merry-go-round. Now first of all, we know, oh, I'm actually going to switch back to my red pen, that's my bad. We know that I is proportional to mr squared, right? Which means the inertia depends on the mass or the radius. Now the mass is not going to change Okay, it's constant. However, the radius will. Okay, so it says here each child moves inwards towards the center. Right, this is the center. If they are moving inwards, right, that means the radius is going to decrease because the distance from the axis of rotation to the outer edge is going to decrease, right? So if we can start our first bullet point with something like this, I'm just going to write it down and I'll cut back to when I'm done. Right, so here's the first bullet point. As each child moves inwards, the mass distribution or radius from the axis of rotation decreases. Thus, the inertia is going to decrease since the mass is fixed. I equals mr squared. Now, the next bullet point we have to talk about is actually regarding angular momentum, because this is our next equation that we're going to talk about, right? So we have to sort of talk about how this stays conserved. So I'm going to cut to when I finish writing the second bullet point and explain it. Right, so I've actually just written a whole answer, but it's easier for me to talk through all of them as a whole rather than individually. So we got up to the second bullet point, which is angular momentum, which is L, is conserved because we're assuming it's a closed system and no external torques are acting at the axis of rotation. Okay, so that's this equation here. I'm just going to rewrite it again. So angular momentum equals rotational inertia times angular velocity. So next bullet point, assuming angular momentum is conserved, a decrease in the rotational inertia results in a proportional increase in the angular velocity since the L is the same, which is what we've just said before. So finally, answering the question, which asked us to explain the effect this has on the rotational energy, we know that EK rot equals half of inertia times angular velocity squared. Now we know that the inertia decreases, but since angular velocity is squared, that means the rotational kinetic energy is going to increase overall. So there's a small decrease in inertia, but that is outweighed by the overall increase in the angular velocity because it's squared. So that is the whole question. It's, it looks quite difficult, but it's not really. There's just three main formulas which I've written out here that can help support your understanding. So you start with talking about the inertia, and you link that to the angular momentum. You do have to make that key assumption that it's conserved, or else you can't really carry on with your explanation. And then sometimes they might not even ask you to talk about the energy. Sometimes they might just ask you to talk about the angular velocity. But if they do, you know what to talk about. So yeah, it's just those three main steps. And this is actually an excellence question. So I'll get my pen out. So all four concepts explained and linked. Well, 4 is also the angular momentum being conserved. I'll just add that in. So all four concepts explained and linked will get you an excellence, so a high excellence, so full answer. An E minus is 3 or more concepts explained and linked, but without the justification of the conservation of angular momentum. So you are missing this. That will get you an E minus, or a low excellence. A mirror is 2 concepts explained, so these two here, or these two here, it's a mirror. And achieved is just any bullet point, I'm pretty sure. So recognizes that inertia decreases here, or recognizes that the angular momentum is conserved, so here, or recognizes that the angular velocity increases because mass is getting closer to the center. So sort of like this part here, but you also sort of have to link it to here. Right, that is question 2 done. I will post question 3 soon, which is about simple harmonic motion. As usual, any questions, leave a comment, and yeah, see ya.